Okay, so welcome, and here we have an example where we have two coefficient matrices, and the first one is non-singular and the second one is singular. Okay, we can tell because we can see that the second row is a multiple of the first row, and this one here is not. So this is a non-singular matrix. This is a singular matrix. Okay, now if we set this up, we can see that there's the same number of variables and equations for this for these. So here we go, x plus 2y equals 0. (3x plus 4y equals 0). And we go here, we go x plus 2 equals, x plus 2y equals 0. 3x plus 6y is equal to 0. We can see over here that this is just going to give us a 0 row. Okay, and so when we're looking at this example, okay, the first has a unique solution. This is going to have a unique solution. This one's going to have infinitely many solutions, and you can see that. We've worked with these before. We can see that this is going to have infinitely many solutions because we're going to have a 0 equals 0 here. And so we're going to have a free variable in the y. So y can be whatever you want, and that's going to determine x. Okay? And that's going to give us an infinite number of solutions. Where here, we're going to end up with a unique solution with the non-singular matrix. Okay? And so we make a distinction in the definition because, now here's the thing, because a system with the same number of equations as variables behaves in either one or two ways, depending on whether the matrix of the coefficients is singular or non-singular. Okay? Now, it's either going to be a unique solution or an infinitely many solutions. And so we can see, and by the way, this is going to have a unique solution regardless of the constants on the right-hand side, because we could just replace these with two different constants, and we can row reduce and solve this. So if I take -3 times the first row and add it to the second row, what do we get? Well, we get x plus 2y is equal to a, and of course -3x plus 3x equals 0. -3 times 2 is -6 plus 4y, so that's going to give us -2y. And then of course -3a plus b. So this is getting -3a plus b. And of course this is going to give us y equals the quantity 3a minus b divided by 2 for y. And then of course x is going to equal a minus 2y, which is going to equal a minus 2 times the quantity that we're talking about here, which is going to be 3a minus b divided by 2. And of course, this is going to cancel with this, and then if we distribute the negative sign, that's going to give us a plus b minus 3a, which is of course going to give us b minus 2a for x. And so there's our unique solution. Okay? Where in this case here, we're going to have infinitely many solutions, and just to give you an idea, this is one solution, right? And another solution that'll work are these two. Okay? Now, let's talk about the word non-singular and singular. Let's talk about the word singular. So a lot of people think, students will think, okay, if I use the word singular, that means, hey, there should be a unique solution. So, and so they're mistaken, okay? The way we use the word for singular means that it's, it is, how do I say this? It's not what we'd expect in general for an equation, for a system of equations with the same number of equations and the same number of unknowns. We would expect that a system of equations with the same number of equations and same number of unknowns would have a unique solution. That's what we generally expect. So when we talk about singular, it's not the way we normally would think about the word. When we talk about singular, this would be something that would be that goes against what is expected. Okay, so when we say have a singular matrix, okay, we would not expect, it goes against what we would expect if it has a, if the system has the same number of rows and columns. So singular matrix, okay, we don't want to assume that it means that there's a unique solution, okay. Singular in this case means that it would go, it's not what we'd expect, okay? In other words, we can look at the word singular saying, hey, this is a troublesome example, or this is a troublesome situation, okay? So when we use non-singular matrix leads us to a unique solution. A singular matrix does not. So it's ironic, right? Because when we think singular, we think unique. In this case here, the term singular is not used that way, okay? So if we have a singular matrix, we're going to have an infinite number of solutions, where if the matrix is non-singular, that's where we're going to have a unique solution. So just keep that in mind. Don't mix the term up. Okay? Other than that, have a great day.